Okay, good morning everybody, and welcome to the next session on ADSP, Advanced Digital Signal Processing. So last time we finished with matched filters, and we also saw an implementation using neural networks using PyTorch, right? Because matched filter is sort of a detector of something or recognizer. And now we want to continue looking at prediction. Right? So for prediction we basically also take a Wiener filter, so we can view prediction as a special case of a Wiener filter, where the noise of our signal corresponds to a shift or the shift of our signal into the past. Right? So our goal is to make a good estimation of the present sample of our signal based on past signal samples. So good here again means in the mean squared error sense. So again, the Wiener setup, just that instead of noise, we have now the future sample. So the noise in our case is looking into the future, and we know that looking in the future is always noisy. We can never do it perfectly. So this is then our Wiener filter formulation for this case. So again, here we have our samples that go into our filter. So basically we wrote the convolution in terms of a matrix multiplication. Here's our input samples, for instance our audio signal, and here are our coefficients, or Wiener coefficients, or in this case the prediction coefficients. And then the output of our predictor filter should be the next sample. So here you can see the predictor has sample number 0 and 1, and it should output sample number 2. So it should predict the next sample that should come in the sequence. So it should make a guess, and this guess should be as good as possible in the mean squared error sense. So here in the next time step it has that sample number 1 and number 2, and then it should predict number 3. Then it has number 2 and number 3, and it should predict number 4, and so on. Right? So it's kind of interesting, right? We have a predictor of future events. So this could be, for instance, used for forecasting stock. So if you're in the stock market, invest in your stock, then you want to know how it develops, so that you know if you should invest more or sell. And you could actually use this to predict the stock market. So you could use this to become rich, if it works. Right? That's the caveat. And actually banks, they use indeed mathematical models, actually more sophisticated than this, but they actually employ many mathematicians who try to forecast the stock market for the bank to make good investments. Yeah, so this is one principle of making such predictions. Forecast. Another example would be the weather forecast, right? Weather forecast, maybe we have a past sequence of temperatures, and then we want to predict the temperature the next day. And again, we could use such a predictor and predict the temperature the next day. And actually, since the weather has kind of a predictable pattern, this often might actually work. When you think about the seasons or day and night, this makes it predictable. So in general, we again have this formulation. We have a tall matrix A times our column vector H transpose, and this should be approximating our target X. And this target X is now the next samples to predict. So this means the input to our filter is always starting at one sample in the past, going down further into the past. So its goal is to estimate or predict the next coming sample. Basically this means that instead of additive white noise, our distortion is now a delay operator. And fortunately, this is a linear operator. So that works. So now we can again use our approach with pseudo-inverse to obtain the mean squared error solution for our approximation. And we saw that this mean squared error solution is this. Right? We have A transpose A inverse times A transpose times our target X. So we just take the same solution as for Wiener Hopf, just for our new target X. Right? For denoising, this X was on our clean signal. Here it's on the signal into the future. Yeah, and A as defined as above. So this now again leads to the statistical description with A transpose A converging to our autocorrelation matrix, as with the Wiener Filter case. So here you can see it again, except that now this X is the clean signal. In the Wiener case, it was the Y, it was the noisy signal. So here we now have the clean signal, the autocorrelation matrix of our clean signal. So the correlation at the different time lags. Yeah, so this is plausible because now y of n is just the delayed signal and the autocorrelation function of the delayed signal is identical to the autocorrelation of the original function. Right? So next we need the cross correlation A transpose X. So in our formulation, since we now have just this one sample in the future as our target vector, this converges to the autocorrelation vector starting at time lag 1. So this is basically coming from the prediction into the future now. So here, this A transpose X converges to the autocorrelation function or autocorrelation vector starting at time lag 1. Yeah. So altogether, the solution for our prediction filter is simply taking the autocorrelation matrix inverse. So remember, this was A transpose A inverse, and times Rxx. Remember, Rxx was A transpose X. Right? Or, yeah, so inverse of the autocorrelation matrix times the autocorrelation vector starting at time lag 1. So this is actually quite a nice and simple solution for our predictor. So now let's continue in the next set of slides, 14. So this is a block diagram of such a predictor. So in comes your signal X, your measurements or your audio signal, for instance. Then this predictor is h of z. So this is our predictor filter now. Right? So I draw it in the z domain, so that's why I'm depicting this as h of z. And this z to the minus 1, remember, means a delay by one sample. Right? So all this predictor sees is the past sample, but not the present sample. Right? It sees everything from the past except the present sample, because this is what's supposed to predict. Right? And then out comes the prediction, x hat of n. And then we can see how precise it was. We just take the current sample, which is supposed to predict, and subtract the prediction from it. And then we get an error, because the predictor is never perfect. Right? We never perfectly know the future. So then E is our prediction error. Right? And this could be, for instance, part of a speech coder, an audio encoder or a speech encoder, where we have audio samples or speech samples coming in here. The X would be samples from our sound card, for instance, coming from the microphone. And then we have our predictor, which tries to predict the next sample, and what comes out is only the prediction error. And if you have a good predictor, then this prediction error is much smaller than the original samples. And when we have smaller samples, that means we can encode them with fewer bits. Right? We have a smaller range, and hence we need fewer bits to encode them. So this is actually indeed a typical setup for speech coding. Right? So for instance, what we have in our smartphones. They use, for instance, this predictive coding setup. sense so far? So this is prediction as used in a coding setup. Yeah, so X is the signal to be predicted. H of Z is our prediction filter in the Z domain, whose coefficients are obtained with our Wiener approach in the last slide set. So here's the solution again, and H of Z is simply its Z transform. Right? So we just take the coefficients and apply the Z transform, and then we have capital H of Z. So this works only on past samples, so it only knows those past samples, and that's why we have the delay element by one sample, Z to the minus 1, before it. And basically we hide the current sample from it. So X hat is our predicted signal, and E is the prediction error signal. Yeah, and that means the output of this system is this. Our system produces the prediction error, which has the Z domain transfer function of HPR of Z, which is 1 minus the prediction value. Right? So you see here, this was the delay element before the predictor, and this is the predictor itself. So this is the output. So basically, we have the input going directly through, and we subtract the predicted value coming out of our predictor. Right? So this is our transfer function of our encoding system. Yeah, so this can be an encoder. Observe that we can reconstruct the original signal X of n in the decoder from the prediction error E of n with this system here. So here we have the error, right? And we obtain the original sample by just adding the predicted value to it. Right? So in the encoder we have signal minus prediction. Here we have error plus prediction. And this returns our original signal. So here error plus prediction gives us our original signal or value, as long as the X hat here is identical to the one in the encoder. Right? So this is the critical part here, that we have the same predicted value in both encoder and decoder. Right? And we can obtain that if we assume that the reconstruction of the past values was correct. Right? Here those past reconstructed values, which are fed into this predictor in the decoder, must be identical to the ones in the encoder. And then this works. But as soon as we have some error coming out here, this predictor sees something different, and then the output will also be different. And then we have more unequal values. So if we have exactly the same values, it works. But if one of those values is corrupted, then this chain breaks. Right? Those two diverge, and possibly they never catch up. That can happen. So that's something to keep in mind. It's kind of sensitive to errors. Yeah, so we have this feedback system here, which makes it sensitive. And we can also formulate this feedback system easily in the Z transform domain, and that's why I chose the Z transform domain here. So the feedback loop in the system is causal because it only uses past already reconstructed samples. And we get the decoder's transfer function as this. Right here we have our feedback loop. So this is basically like an IRR filter. And we know that this IRR filter appears in, or the IRR part appears in the denominator of our transfer function. Right? So this is then the result. If we have this feedback loop, in the Z transform we bring this on the other side. There was already 1, so we have 1 minus this loop part here. And we see that this is actually identical to the transfer function of the encoder. So here this is 1 over the prediction error filter in the encoder. So when you look at it, so was the encoder formulation. So the decoder is actually exactly doing the inverse. So we have exactly the inverse of the encoder, which was to be expected, because that's what we want, right? We want a reconstruction. Yeah, so now a Python example. We take a prediction filter, or construct a prediction filter for our female speech signal, and use a prediction order of L equals 10. Right? 10 turns out to be a good number, sometimes also 12. So we chose 10, and we use the setup that we just saw, which minimizes the mean squared prediction. So this is then our code. So we can take a look at it first. So we do it again in IPython and using PyLab. So everything is done in the Linux shell interactively. Here we import our sound library, which reads and writes speech. Here we read it in fspeech.org, and we can see how many samples it has. 207,000 samples. Right. So then we make it a matrix of flow type and transpose it into a column, normalize it to be in the range of -1 and 1, and this is what's done here. So we turn it into a matrix type, because that makes it easy to use our matrix formulation that we just saw. So X will become a matrix using the data type float. Here I transpose it, so I make a column vector out of it, and here I divide it by the maximum value that come out of 16-bit integer. Right, remember, 16-bit integer gives you a value range between -2 to the 15th to +2 to the 15th. Right, so then after this division, we will have this range between -1 and 1. So for checking, we can listen to it. Again, turning X back into a one-dimensional array for playing it back. So here, basically, we turn it again into array and we denormalize it just for checking, right, to see if everything works. So maybe we can start. Let's see if my IPython 3 works. So here I open simply my Linux terminal shell. And type IPython -PyLab. IPython, let's see, IPython 3 -PyLab. I'm not sure if that works here. No. So if Python 3 is not working, then usually Python 2 is working. Yeah. So now next line, from sound import everything. And now the next line here, I just copy and paste it. Control C, Control Shift V. So now we have X, and you can see the shape, which I'll type the shape of X. So indeed, we have 207,000 samples, and this is interpreted as a row array. You can also type just X. See, this is what we get. So we have an array. The beginning samples will be 0 because it's silence, and then here it's doing something in the end. And a data type of integer 16-bit. This is how it comes from the sound card. Now, then the next is we change the data type and normalize it. Copy, paste. So now it's normalized. And now we do the checking by playing it back. And for playing back, I should use my active active speaker so that you can hear more. So,
Bluetooth mode.
yeah, so hopefully it's connected now. So now I'm using my sound command here to play back.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
Yeah, that was easy, right? Got everybody here. So now we make our filter, starting by constructing our matrix A. Remember, this was a tall matrix where each row contains the 10 past samples. Right? And the lower we get, the deeper we get, the newer the samples will be. So this is what we do here in this for loop. We begin by initializing the matrix with the right dimensions, with zeros, and then I have this for loop which goes over all the rows of the matrix. So each row gets 10 samples of our signal. So here you can see a range 10 is the numbers from 0 to 9. Right? And we start at n. So in the beginning, this n will be 0, so the zeroth row will start at sample number 0. The first row, row number 1, will start with sample number 1, and so on. Right? So each row will start one sample later. And this is then assigned to A. So I can hopefully just copy and paste. Let's see if it works. So you could see it actually took a second, right? Because it's actually a large matrix with 100,000 rows. So it actually took a moment to fill all those 100,000 rows. So when we take a look at A, this is what you get. So this is now the last row of A. You can see here we get small values because this is kind of the end of the file. Just a few noise samples basically. And we can also type shape of A. Then we will see indeed it has 100,000 samples and 100,000 rows, and each row has 10 entries. Yeah, now we need to construct the desired target signal, D. So this is one sample in the future, and we start with the first 10 samples already in the prediction filter. Then the 11th sample is the first to be predicted. Right? So this is how we constructed our matrix A. Remember, we could also say before the first sample counts only zeros. Right? That's also a possibility, but we didn't do that. Right? We really filled it up right away. And this is usually also what you do, because this assumption of having zeros before the beginning of a signal may be good or not. Right? We don't really know. So that's why it's always a good approach to not making this assumption and really start with filling this matrix right away with the signal samples that you have and not making any assumptions of what came before. And that means we also need to start our desired vector here at sample number 10. Right? Remember, sample number 0 to 9 is already in our predictor memory, in A. So the next unknown sample is sample number 10. So that's why we start with 10 here. And we go up to sample number 100,010, excluding 100,010. So up to 100,009. And also observe that we only take the first 100,000 samples here to make the prediction fit, not the entire 207,000. Right? So I'm taking the first 100,000 samples in this case sort of as a training set. Right? I use this as a training set for my coefficients, H, but I then can apply this filter to the entire file. Right? So basically I'm taking the second half of this audio file as a test set, where I see how it performs. Yeah, so here is now my desired vector, which contains for each row the next sample. Copy, paste. So this is our D. So you can see those values should not be in A. So here A has the last value of 1.9 minus 1.9 times 10 to the minus 2. And it's indeed not appearing here. Yeah, so these are the samples in the future for each row. And now we can compute the actual prediction filter. Right. So here we can see our formula. So here we can see we are not taking the statistical formulations, the autocorrelations, but we really use the A matrix because we now have it. Right? You can use the statistical formulation if you don't really have the signal itself, or just the statistics, but here in this case we really have the signal, and then we can use it, because then it actually gives us, it's more convenient and also gives us a more precise solution, instead of having just the correlations. So that's what I'm doing here. So that's also why I took the matrix type, because I simply can use this formula from the slides above. It almost looks identical in Python using the matrix type. So that's really convenient. So here's the formula. We don't really need the semicolon. So now it's done. So this was really quick, right? So observe that this was actually much quicker than constructing the matrix A. So the longest time it took was making this matrix A. So now we can take a look at H, and this is what we get. So let's see if it's the same. Yeah, as expected. So now we have our predictor coefficients. So it's kind of hard to tell if it makes sense. So we can basically test it, or first take a look at it using our plot function. So here we now plot it, see how it looks like. So this is what we get. So what do you think? Does it look good? It's hard to say, right? It doesn't really look like a low-pass filter or something, right? A low-pass filter you would expect like a main lobe and then some side lobes. Here it seems like you have one peak, then you have another peak, and you change quickly. Kind of hard to say. They look kind of interesting. Yeah, so this is our impulse response, and it has this funny shape. But maybe it does a good job. Right? Maybe it really is a good predictor. And yeah, we could also guess, because here at sample number 0, we have a very high value. So this predictor actually places a high confidence that the past value is very similar to the future value. Right? So that's why it places a high value to it. Interestingly, the next sample, it thinks it has the negative sign. So, yeah, so then our prediction filter with a delay in the encoder becomes this. So here we have, this is V stack, vertical stack. So we start with a 0, and then we have our coefficients coming after the 0. So basically this is the delay by one sample. Right? So this is the delayed prediction filter in the encoder. Remember we have the z to the minus 1 times the prediction filter, and the z to the minus 1 shows up as the 0 here. Right? So it's basically delaying the impulse response by one sample. Yeah, so the predicted values are now obtained by applying, should be L is the time function, by applying these coefficients as an FIR filter. So we have this prediction filter in the encoder with this delay, and we can simply apply it using L filter, which we already know, right? Here is the B coefficients, the FIR part. We are not using the IRR, the feedback path, that's why this is a 1. And this is our input signal, now cast back as an array. And we also need to turn this into an array because that's what L filter expects. Right? L filter doesn't like the matrix type, it wants to have the array type. So that's something to keep in mind. So that's also why in general I try to stick with the array type, except if I want to make really matrix calculations like in this case. And also we need to make this one-dimensional, that's why I have this 0 here as an argument. Right? Because H is a matrix type is always two-dimensional, right? Even if it's a column. If it's a column vector, it still has the other dimension, and that's why I need to add this argument. First dimension index 0, and then the rest is the one-dimensional array. Same here for x. I turn it into an array. This will be two-dimensional, so I need to remove one dimension by specifying here this argument 0 for the first dimension. Make sense?
When you make the H prediction matrix and transpose it, then the rows will be 0 only. So why are we making it an array? If you transpose the H prediction matrix, it's a column matrix and it converts into a row matrix, so it would be 0, the other rows. Is it necessary to make it an array?
You mean in this place here?
The previous one, H prediction matrix.
Yeah.
As we've seen, it's a column matrix, the result.
This one here?
Yes.
Yeah, this is a row matrix actually, a column matrix.
Yes.
Yeah, right, so vertically.
And when we do the transpose, it will convert into a row matrix.
Yeah,
So
exactly.
it becomes an array in itself, and why are we converting it to an array?
So here it's still a matrix type, right? So here you see it's a matrix, right? And the matrix always has two dimensions. So this has a dimension of one row, one column, and 10 rows. Right? Yeah, 10 by 1, right? 10 rows, 1 column. So actually we can see it here. I type in shape of H. So 10 by 1.
It still has to.
Yeah, and right. So it comes out of this formula as a matrix type. So when we turn it into an array type, then it has the same shape. Right. So when we type shape of array of H, we have the same. It's just a different type. Right. So yeah, I'm not sure. Is that what you meant?
Yeah, that why are we doing this if they are the same size? Then why are we converting it from matrix to array? Just to convert the type?
You mean here at this point?
Because the L filter function is an array. It doesn't work if it is a matrix type. So
Yeah, right. So we can also take a look at the result of H. So then you have array of H, this is what we get, and array of transpose, and we transpose it here, we get a row vector, and then when I say 0, then basically one of the dimensions disappears. I'm not sure what happens if I omit this transpose. Maybe it still works if I don't have this transpose here. No, you can really get just the first sample. Right?
it's, maybe because you need to write a 1 instead of 0.
Yeah,
Then you
I guess I need to write it like this. Yeah, that works. because then I'm removing the second dimension. Here I keep the first dimension and remove the second dimension. So this also works. Which one do you like better? This one or this one? I guess it doesn't matter. So here we now have the prediction of the predicted samples at the output of the predictor, and because of the delay, the predicted samples are synchronized with the original samples. So the predicted samples now don't appear one sample earlier, but at the same place as the original samples. And that's also why we can subtract them. So let me first calculate this one here. Response. This now works. So now I have this delayed predicted sequence, and I can plot the original and the predicted on top of each other. So here's original x, and then I plot the predicted in red on top of each other. And then we can see how close they are. Right? When we see they are very similar, then we are good. So this is now a test of our predictor. Since the impulse response was kind of hard to tell if it's good or not, here we can really see if the prediction works. Because we have the original, and then we have the predicted values at the same place. So for each sample we can judge how good it was. So, copy. Here you can see it. So the red here is the predicted. The blue is the original. So what do you think?
It's not that bad.
It's not perfect, right? So actually here we can zoom in. So we just have a broad overview looking at this picture, but let's see, zooming maybe here in this area here. So here we have two types of signal. You can see this is oscillation mode, more or less, right? And you can see here where you have this oscillation even here. It predicts quite well. It's almost perfect, except here for the ends. There's a little difference, but it's actually amazing how well it predicts, right? But then here you come into a more noisy part of the signal. And then you see it's harder to predict. It still does a pretty good job here. But you see it's not as good as here in this more periodic part. And that's a problem in general. When you have tonal parts of the speech here, that makes it quite easy to predict for the predictor, because it's periodic and it repeats. But then if you have plosive parts like S and T, and it's more like a mix of noise and oscillations, and the noisy part is hard to predict. So the noisy part is basically filtered noise. Right? So the filtered part you can predict with the filter, with the prediction filter, but the noisy part you cannot predict. Right? Because the noise which you assume is the input of your filter is white noise, which means the samples are uncorrelated to no memory, and that's something that's impossible to predict. So this is the limits of our predictor. If we have noise, noise cannot be predicted if we have white noise, uncorrelated samples. And that's also the problem of predicting the future. There's always noise in the future, and you cannot predict the noise. Right? You can predict the predictable parts, right, but not the noisy parts. Yeah, so I would say this is actually quite a good predictor. It's doing a good job. So now we can also make a prediction error filter to compute the prediction error. But I more clearly see where it does a good job or not. Right? So here we make this prediction error, which is just the difference between the original and then the delayed prediction filter. Right? So we just take the picture that we just saw and take the difference between the two curves and plot it. So here's first our filter, this prediction error filter, which just takes the difference. So here we have, instead of a 0, we have now a 1, because we want to keep the original. And then here for the prediction filter we have a minus sign, because we want to subtract now the predicted values. So copy, paste, and then we can take a look. HPR, these are the coefficients. So we can see indeed they are identical here. Right. So this is now our prediction error filter. Again, a color matrix. So now we can simply put it into our L filter. Right here are now our prediction error coefficients. The rest is the same. So here the IR part is not present, and here is our input signal. Right, so same L filter setup, but just different filter. Now the prediction error filter. So right here I turn it back into the matrix type, and here I'm computing the power, the error power per sample. So here I'm taking E times E transpose, so E is a row vector, E transpose is the column vector, so this will be a number, sample squared plus sample squared and so on. That's why I divided by the number of samples, here max shape, I need the max because I get two values for shape, right? So the larger one is relevant because that gives us the number of samples. So here I'm dividing by the number of samples, and then I get the mean squared error from this prediction. So let's try it, see if we get the same result. Copy, paste. Yeah. So this is our result, and indeed it's identical. So this number itself doesn't really say so much, we need to compare it to something. And that's what we do next. We compare it to the mean power of the signal. So mean squared signal power per sample. So here I'm doing now the same for x instead of e, and we get a new output. So let's do that. Copy, paste. So here, indeed, we get again the same value. 0.0069, and now we can compare. Right? So when we compare those two values, so we can see here 0.0004, so we have 3 zeros, and for the x we have 2 zeros followed by a 6. So that means the power from the signal per sample is more than 10 times as big as the power from our prediction error. Can you see that? So that's kind of interesting, right? So it's more than 10 times as big as the prediction error. And this shows that it works. Right? We see that the prediction error is indeed much, much smaller than the signal itself. And this is beneficial, for instance, if you want to use it in a program. Right? Because the signal values will be much smaller. So to see how big they actually are, we can play them back, right? So instead of playing back x, we can just play back e. So maybe as a comparison, I first play the original. Sound. See, this is auto-completion. I just type the first few letters and then I type up arrow and then it auto-completes. Quite convenient. But it's only IPython which does it. If you have Python, it's not doing it.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So this was the original, and now as a comparison, the prediction error. Copy, paste.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
Oh, it didn't sound so bad, right? No. So now we can also take a look at it. Yeah, you could also hear that it sounded more high pass. So now let's take a look at the plot. First the prediction and its prediction error. So here the signal itself. Plot 2 to the 15th times x. Then the same for e. And here I'm setting up the axis and the legend. See what we get. So this is the result. So we have the original. Blue is the origin signal and red is now the prediction error. And now you can see that indeed in those areas where we have plosives, you have bad prediction. Right? Like this region which we looked into before. So here we have a high error in the region where we have plosives, which means it's hard to predict. Noise is hard to predict. Right. So this shows you it works, but maybe it's not so great, because also when you listen to it, the difference was not so big, right? Yeah, so the decoder uses the reverse filter structure, which we already saw. So remember, this was the decoding structure. Again, just a different filter. So here for the reconstruction, we can simply take, again, this L filter, but now instead of putting this HPR in the numerator, we now put it in the denominator. Right? So now the FIR part is just 1, so it's just going through. And here is the IR part, so this is the feedback. Right? And the input is now not the signal X, but the prediction error. Remember, E was obtained by filtering X and having this filter here in the forward part, in the FIR part. Now we have E filtered and we put the same coefficients in the IR part, in the feedback part. So it should cancel. Right. So this is what we're doing here. Yeah, so this is the reconstructed. And you can see that you only see red, right? Why do we only see red? Yeah, because it's the same, right? It's indeed identical. So I can also zoom in. Closer. So it's always indeed just red, because it's identical to the blue one. So that means we have perfect reconstruction here. You can also listen to it. Copy.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So this sounds exactly like the original. So you can compare it with the E. So here instead of X rec, I'm just taking E. Oh, I missed a bracket. What did I do wrong? Data type not understood.
Yes, because you need to put them error.
Ah, yeah. Right, the wrong bracket. Thank you. So this should work, right? No.
You're using two channels. There should be one
Yeah.
channel.
Yes. You need a 0 after this.
Yes, I need a 0. Yeah, like here.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So this was the prediction error, and the reconstructed was this.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So you can hear this is much louder, right? So it has more amplitude. And also here you have the low frequencies back, right? And this is because the low frequencies are easy to predict by our predictor, because they're periodic. Yeah, so here we can see that the decoded, reconstructed signal looks and sound identical to the original, as expected. So this means we can indeed use it in an encoder-decoder set. So add signal here. Yeah, and interestingly, we can also use it in a neural network implementation. Right? Again, it's an optimization task. We have training data, we have a target. So we can use the numerical optimization of PyTorch instead of our closed form solution from Wiener and a conf1d layer for the filtering. Right? We also use the mean squared error, we can do that, as minimization criterion or loss function. But remember here we are not limited to mean squared error. We can also use other types of errors because they are available and because we are doing numerical optimization. That's different from Wiener Hopf. Wiener Hopf relies on the mean squared error. The closed form solution only works because of the mean squared error. Right. Here, basically, we can choose different loss functions. For instance, absolute error or test minimum. So that might be something that might be more suitable for audio coding or speech coding, for instance. In this case, this does not differ from the target of the closed form formulation, and hence we obtain almost the same solution, right? Because we chose the mean squared error. So here the desired target signal y is the audio input signal x, but one sample into the future. Right? Same setup as before. So here we have x, which is our audio signal. Here we remove the last samples for the convolution. Right? So L is again our filter length. Then here we have our target signal. We start with sample number 1 and not with sample number 0. Right? So then I wrote it in this Python program here, which we can take a look at. Copy. Quit. So gedit. So this also shows you how to program neural networks using PyTorch. So here you can see the beginning is as we're used to it. Then this is not really important. Here is the setup, the filter length, dilation is 1, which I'm basically not using. Dilation means upsampling of the impulse response of the filters, which you can do with neural networks. Sometimes it's useful, but we're not using it. And here I'm having a function which turns a vector from NumPy to PyTorch. Right? Because PyTorch has its own data format which it uses. PyTorch uses PyTorch tensors, and they might have for instance, gradients associated to it, which is important for optimization. So here I'm starting with the input vector, and here you can see I first add dimensions to it. So first I add the batch dimension. So batch is used for training large data sets, where you basically load one batch at a time. And then the next dimension is for, I think it's another feature dimension. So we need, right, you can see it here, batch, signal. So we have two dimensions. Add batch dimension and add another dimension here. Yeah, this is kind of tricky because the meaning of the dimension also depends on what types of neural networks you're using. So you actually have to check it each time in PyTorch. So here then I'm taking this now three-dimensional vector and turn it into the torch type. And here a torch tensor type. And then I return this torch tensor here, which neural networks can then process. Makes sense? So the most important part are the last two lines here, where you do the type conversion. Then I define my neural network as a class. So in PyTorch, you define your neural network as a class, which then makes an object, which you initialize with some desired parameters, hyperparameters. So here you can see the class called conflict. Here's the init function where you can set up with certain parameters, the hyperparameters. So in our case, it's the number of input channels. Here we have just one, because we have just some mono input. The number of output channels is also mono output, just one channel. The kernel size is the filter size, the filter length. Right? So that's also a different term, different terminology. What's in PyTorch kernel is in signal processing the filter. Right? So that's something that you have to remember. So here our kernel size, the filter size is L, and L was 10. Stride here is the term from neural networks for downsampling. Right? What we call downsampling in neural networks is called stride. And that's kind of interesting because different fields sometimes use different terms for the same thing, and that's often because they came from different backgrounds. Yeah, dilation was one. Padding here is interesting because this involves zero padding. And here I'm actually using a padding of L-1. So in this case, I'm actually adding L-1 zeros in the beginning of our audio file. Something that I advised you before not to do because we have the A, right? So here I did it anyway. So I'm adding L-1 zeros, and this makes the filter causal. So that's the advantage. When you have L-1 zeros before it begins, then it means the output of your filter will always be in sync with the input. Right? And this is basically beneficial looking at the indices. Bias equals false. Do you know what bias means? This is just the fixed values which might be added. And this is common in neural networks, but we don't need it here, right? Because we just use it as a normal convolution. So we don't use the bias, and that's why we said bias equals false. So it's convenient actually to have this option to remove the bias. Yeah, and this basically sets up our neural network, and this is operating on it. So here this forward function, right? So the forward should always be there. Self means our class here, and then X is the input. So X will be our audio signal, and then it simply applies this layer 1 to the audio signal and returns the output. And usually in neural networks you would add in nonlinearity after this convolution layer. which we again don't do here because we really just want to have the convolution. And it's actually convenient that we can omit this nonlinearity, which is called activation function in neural networks. Right, so here we just use PyTorch as a toolbox, and with the optimizer that it provides, without really having a full neural network. It's basically a simplified neural network, and all what's left from this neural network, this convolutional neural network, is this conv1D, this one-dimensional convolution. So this is a convolutional neural network minimized, right? The minimum form of a convolutional neural network. So here's the class definition, and then here in this main section, which is executed when we start this program from the terminal shell, then we see that it reads in our fspeech file. Here normalize it again, like we did. Here we just create an excerpt of the first 100,000 samples as before. Then we plot it. And here we change the format. So here we turn it into a PyTorch format. So we take the short one, and we don't go right to the end. We actually stop at n-1 samples before, right? Because that's what we need for the filter. And here's the target starting at sample number 1. Right? So we remove the first sample. Make sense? So this is our input to our neural network, this convolutional neural network. This is the output, which is just the same, just one sample in the future. Yeah. Then here it prints the shape that we get from after the conversions. And here we actually create now the object. Model equals convnet. So convnet is the class that we defined above. And now model is the object containing our neural network. Right. So this model now contains this forward function which we need. And next we define the loss function. You can see the loss function is mean squared error loss. And here we define the optimizer. Here we take the ADAM optimizer, which is basically gradient descent with moments. That's why it's called ADAM, adaptive moments. And here's now the actual optimization. So this is what we didn't need with Wiener because we had a closed form solution. Right? But now we need it here because we don't have the closed form solution. And here you can see it makes the first prediction from the model. So model of X. So strictly speaking, we would have to write model dot forward of X. But PyTorch is made such that forward is the default if we don't specify anything. Right? But strictly speaking, this should be model dot forward. So here is the predicted values. And now we can compute the loss between the predicted values and the original values. Right? And then we can minimize the loss, which is done in the next steps. So here we see the current loss. And here we have the optimizer step. So initializing gradients. Here the backward step, basically using the chain rule from the output towards the input for the gradients. And then here the steepest descent update. Right, so this is the gradient step. Here it updates the coefficients, the weights, or the coefficients of our filter. Make sense? So basically this is gradient descent, those 3 steps here. Still remember gradient descent? Did we have gradient descent? Not really. Did you? Oh. Yeah, so this is basically this standard gradient descent which you see here. Except that it's ADAM, so it includes moments, adaptive moments. So we do this here 6,000 times. So it's actually quite a lot, right? 6,000 steps, 6,000 times over and over. But after 6,000 steps, we have a good solution. And then we can save our weights here using torch save, and the weights are in model stage dictionary here. This is basically the part that contains the weights, which we then can store into file. Yeah, and then we can process the full length signal. So here I'm using the same conversion, but now using the full length audio, not the short audio, for testing. And now I'm making the predictions again, now with a model with a fixed or with a finished coefficients, right here at this point. And now we can compute the same error and signal power here as we did before to compare. Right. And here we can also see the obtained weights. So model state dict contains the weights. And here I'm printing the weights of layer 1 weight. So this is a dictionary which contains the weights which we can then plot. So here we can see the weights, and again we can compare the weights to what we obtained before. So except for the zeros in the beginning, it should give the same output. So here we see plotted the predictions. Here you can see I converted back to the NumPy type. Detached means I remove the gradients from it, and then I turn it into the NumPy type, and I remove 2 of the dimensions. Same here. So this is my original predicted, and here original prediction error. Right? And finally the weights. Make sense? Then we can let it run and see if it works. So Python 3. So this is the audio to predict. So now it runs. You can see it takes a few more seconds, right? It takes longer than setting up the matrix A. That's the advantage of having a closed form solution, right? It's faster. So these are then the weights. What do you think? Are they good?
It's like before, just the other way around.
Yeah, it's time reversed, right? And this is actually a peculiarity of PyTorch. When you have a convolutional layer, even though it's called convolution, it's doing a correlation, which means it's a convolution with a time reversed impulse response. And this is what we see here. Right? It's just time reversed. So it's basically okay, you just have to keep it in mind. Right? When you look at such a picture, you have to know that this is the time reversed impulse response. Yeah, and this is the original and the prediction error. What do you think? Looks pretty much the same as before, right? So this is now the original and the predicted. No, it's also pretty much the same, right? So that's good. That's what we wanted. So here we can now see the evaluations. We have the mean squared prediction error. Here we have 0.0004. This we're missing the last digits, but it's not so important because you see we have those 3 digits, 3 zeros, and then the 4, the same as before. Right, and then for the mean signal power, we had 007, so now we have 2 zeros, and then we had a 6, 8 before, and now we have a 7 here, so basically it works. So then we have a signal to error power ratio of 16, so that should also be the same as before, and here we can see the weights, which we just already saw in the plot. So you can see we have a dictionary here. So here we have the names to address the different layers. So layer 1 dot weight is the first layer, and if you have more layers, then you have layer 2 and so on. Right. Okay. so that worked nicely. So this is actually an alternative to obtain the coefficients, especially if you have more tricky loss functions. And it's also an advantage if you want to use it as part of a neural network anyway for machine learning somehow. Right? And this is convenient because it's already in PyTorch. Yeah, so the next step would be online adaptation. So far we calculated the prediction coefficients for the entire speech file, right? Or in this case, the first 100,000 samples. But we saw that the statistics or the properties actually differ in different pieces of the signal. So some are more high frequency, others more low frequency, some are more tonal, some are more noise-like. So that's suboptimal, taking such a long signal and just applying the same prediction coefficients all over the place. So, because when we look at the signal waveform, we see that its characteristics and hence its statistics is changing. It is not stationary. Right? Hence, we can expect a prediction improvement if we divide the speech signal into small pieces for the computation of the prediction coefficients, pieces which are small enough to show roughly constant statistics. Right? In speech coding, those pieces are usually of length 20 milliseconds, and this approach is called linear predictive coding, or LPC. So before computing the coefficients, we subdivide our speech signal into 20 millisecond pieces. So here the prediction coefficients are calculated usually every 20 milliseconds. So it's 50 per second, right? So we have 50 times per second we calculate the coefficients. So it has to be really fast. So something like PyTorch that we just saw, we cannot really do 50 times per second. Right? It's too slow. So we have to do it every 20 milliseconds and then transmit the coefficients alongside the prediction error, right? From the encoder to the decoder, because we need to make sure that the decoder has the same predictor. So here's a Python example. So we have a speech signal sample at 32 kilohertz, and hence a block of 20 milliseconds has 640 samples. Right? So we write a Python file with the name LPC example with this content here. So this now needs to do the subdivision into blocks. So the beginning is as usual, same here. Here we play back the sound for checking. Again, 10 predictor coefficients. Here's the length of our signal. Here we set up the prediction error variable. Here's the number of blocks that we have. So the signal length divided by 640 samples is the number of blocks that we have. Then here state is the memory state of our prediction filter, because now we have different blocks and changing coefficients. So we need to apply our L filter to each block separately. But if we go from one block to the next block, we don't want to lose the information of the past samples. Right? When we go across the boundary, we still want to access the past samples from the previous block, as long as our filter is going over this boundary. Right? And this is done using the state, which contains this information. So this is the memory state. Yeah, and here is our matrix A. So now we have two loops. One is M for over the blocks, for the range of blocks. And here you can see it initializes this A for each block, which is now having a height of 640 minus L. Remember, L was the filter length. So, and this is the block length. So it's now not as tall as before, it's shorter because the blocks are shorter. Right? And again here, 10 wide. So up to 630 to avoid zeros in the matrix. Right? So it gives better results actually. So for n in range 0 to 640 minus L, so this is the block, we now construct our matrix A. Right? So each row contains our 10 samples as before. And now we have m plus 640 here, plus n. So this is the start of our block. So for each block, basically we have to go one block further. Right? So the same for the D, the desired samples. Here's the start of the block, and here are the next samples, starting with 10 in the future, because we want to predict the next one, which the filter does not see. And then here we have our H, our coefficients. And here you can see, now I used the array type instead of the matrix type for a change. And that's why this formula looks a little bit more complicated. Matrix type in such kind of computations has its advantage. That's more compact. So instead of a star, I'm having to use this function dot. Right. Dot is the matrix multiplication. So here, instead of dot t, I have to use dot transpose. So I have A transpose times A. So here dot is the matrix multiplication function, multiplies A transpose times A. Then here np_lim_alt.inf is this inf function, the inverse function, which I apply to the result here. Then here I multiply it with A transpose and D. Yeah, then I'm done. Make sense? Basically the same as before, but now with the array type. Here's now a prediction error filter as before. So here it subtracts the current value and the predicted value. And here it computes now the prediction error for each row, for each block. And so here, block index, and here you can see the filter, L filter, here the prediction error filter, here the feedback path, which we are not using, here the input, which is one block of our signal, and here we get the previous state as input. And L filter then also outputs the state for the next block. So that's also convenient from this L filter function, that it outputs the state and it reads it in for the next block. So that makes it possible to conveniently process across block boundaries. Yeah. Does it make sense? So your output state at the end of the block, you input it at the beginning of the next block. Yeah, and in the first block, state will be 0. So let's see, do I have it initialized here? Yeah. So here you can see this is for the first block, L zeros. Yeah, so here we have the prediction error, and then we can compute the mean squared error of the prediction error. So here the average, again, E transpose times E, matrix product, and divide by the number of samples. So this is the average squared error per sample. And you can already see the result. 3 zeros and a 1 instead of a 4. Right? So it's actually 1/4 of the previous error. So that's actually quite good. And then compared to our power of the signal, of course that's the same, right? Because we have the same signal as before. So that means we have the signal to error ratio as this number divided by this number is 61. So that's quite a lot, right? So we have a signal to noise ratio or signal to error ratio of 61. So that means the prediction error energy is more than a factor of 61 smaller than the signal energy. Yeah, then we can also listen to the prediction error signal here, and we plot the signal error. So it should sound and look different because it's just 1/4 of before. And then here we continue with the decoder. Decoder is basically just applying the same filter as before, but now in the denominator. So this is the feed-forward part, FRR part, this is the IR part, the feedback part. So this is the reconstruction filter, and we apply it to the blocks of the prediction error. So basically the same as before, but for each block we have to construct the corresponding prediction filter. And so here you can see the H contains the block index M. Right? So this is different from before. Each block has a different set of prediction coefficients. And only that's why it works so well. So now we can execute it and see what it does. Copy.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
Original. Prediction error. It was pretty good, right? It was hard, even hard to understand. And that is because now we have so little error. So here you can see blue the original, and red is the prediction error. And yeah, you can see here, it's indeed much smaller. You see some peaks here. That's maybe this crackling noise that you sometimes could hear. But in general, here it looks much smaller than before. But I think it's easier to hear than to see.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
Yeah, it was able to reconstruct it from this little noise that we heard before. Right? So what we just heard is based on this noisy signal that we heard before. It's kind of amazing, right, that it works. Yeah, so here you can see the plot that we just saw. Yeah, so we see that the prediction error is even smaller than before, and the decoder works in a way as shown in the previous example, and the reconstructed speech can be heard in the end. And as LPC type coders are, for instance, speech coders where usually 12 coefficients are used for the prediction and transmitted as site information every 20 milliseconds. Yeah, and the prediction error is then parameterized and transmitted as parameters with a very low bit rate. And this kind of system is used, for instance, in most digital cell phone systems. So if you want to go to a low bit rate, then you actually take this prediction error, logs of this prediction error, and apply vector quantization to it. Quite sophisticated vector quantization, and in this way you can go down to a few kilobits per second and still understand the reconstructed decoded speech. So this is actually quite a powerful system for speech coding. So when you talk to somebody on your cell phone, most likely it uses such type of encoder, speech coder. Yeah, questions at this point? Make sense so far? So then basically I will leave this for next time. Least means where's. Yeah?
So like what are the filter will be applicable to like the female voice only up to a certain extent? It won't be applicable to if a male person is reading the same text or
Well, it would. So here in this example, you saw that the encoder constantly computes the coefficients. Right? So it doesn't depend on the training set. It really takes the current block and computes the coefficients on the current block. So that's actually a good point. So my first example really had a training set at fixed coefficients. So then we had this problem, right? It depends on what type of signal you have. But here, another advantage is that by using those blocks and transmitting the coefficients as site information, it's less dependent on a training set because you don't need a training set. Basically, your training set is your current block. But as the disadvantage is that you have to transmit the coefficients constantly. Right? And that, of course, costs bit rate. So there's plus and cons, right? Pros and cons. Yeah, good point. Okay, so then I will lead keep this to next time. So thanks for your attention and have a nice day.